Think about something as simple as picking up a cup of coffee. Your hand just goes. It moves smoothly with the perfect amount of force, and it stops at exactly the right spot. It's this incredible neurological dance that we do thousands of times a day, and honestly, we take it completely for granted.
But what happens when that system goes haywire? What if that finely tuned control system in your brain just loses its balance? I mean, imagine having either way too much movement or not nearly enough. That's the core issue we're going to dive into. What happens when your body's internal accelerator and brakes just get their wires crossed? So at the very heart of all this, you've got a crucial player, the basal ganglia. Now, this isn't just one spot in the brain. It's a whole team of structures, deep inside, all working together. And their main job? They're the master regulator, the quality control supervisor for every single voluntary move we make. But here's the surprising thing about the basal ganglia's job. Think of it less like an engine and more like a gatekeeper. It doesn't actually come up with the idea to move. That comes from the cortex, the thinking part of your brain. Nope, the basal ganglia's job is to look at all the possible movement plans on the table, give the green light to the right one, and, this is just as important, say no to all the others. It lets the right move through while shutting down all the unwanted noise.
And this amazing system can fail in two totally opposite ways. On one side, you have hyperkinetic disorders. This is where you get way too much movement. The best way to think about it is that the brain's brake pedal has failed. The system just can't say stop anymore. And then, on the complete other side, you have hypokinetic disorders, where there's too little movement. Here, it's like the brake pedal is stuck to the floor. The system is just pumping out way too much stop signal, making it incredibly hard to get anything going.
So let's start with that first scenario, right? The brakes are off. This is the world of hyperkinetic disorders, where the brain's biggest problem is that it has lost the ability to suppress things. It just can't veto those unwanted movements anymore.
A classic example of this is a condition called chorea, and the name itself actually comes from the Greek word for dance, which, well, it gives you a pretty big clue as to what it can look like.
So what you see are these brief, irregular movements that don't really seem to have any purpose. They just kind of flow from one part of the body to another in this unpredictable, almost dance-like way. One of the key features is something called motor impersistence. So for example, if you ask someone to stick out their tongue, they just can't hold it there. The system simply can't sustain one single, simple action.
But that brings up the big question, right? Why? Why are the movements so jerky and unpredictable? What's actually breaking down inside that gatekeeper system to make this happen?
Well, it really boils down to a loss of that stop signal. Because the basal ganglia's veto power is so weak, all these random competing motor plans that should have been shut down suddenly get a green light. The brain starts activating these little fragments of movement totally out of the blue, all because the filter that normally keeps them in check is just gone.
Okay, but what happens if that loss of suppression gets even more serious? Well, that takes us to an even more extreme example of failing brakes, a condition called bullism.
And here, the loss of inhibition is severe. I mean, we're talking about violent, large amplitude movements. It's often described as a flinging motion of an arm or a leg, and usually it just affects one side of the body, which is a condition we call hemiballismus. So what's the difference? Why is chorea sort of like a dance, while ballism is like being thrown around? What specific part of the braking system has to fail to cause movements that are this violent?
The answer is incredibly specific. It actually comes down to damage to this one tiny structure called the subthalamic nucleus. You can think of this little nucleus as the master brake pedal for the whole system. It's a powerful amplifier for the brain's stop signal. So when you lose it, you don't just weaken the brakes, you've basically cut the brake line entirely.
Okay, so we've seen what happens when the brakes fail completely. Now let's completely flip the script and check out the opposite problem. What happens when the brakes are stuck on? This is the world of hypokinetic disorders, where the biggest struggle is just getting a movement started in the first place.
And the absolute classic example of a hypokinetic syndrome is Parkinsonism. With Parkinsonism, the whole system is biased towards stop, and that makes every single movement feel slow, effortful, and just plain difficult to get going.
Parkinsonism is really defined by four key things. First, and this is the big one, is bradykinesia, which is just a fancy word for slowness of movement. Then you have rigidity, which is this internal stiffness or increased muscle tone. There's often a tremor, a shaking, that's most noticeable when the person is totally at rest. And finally, you get postural instability, which, as you can imagine, leads to serious problems with balance.
So this gets us back to that crucial why question. Why does everything become so slow and so difficult? What's going on in the brain circuits to make that brake pedal so incredibly powerful?
And what's wild is that this huge slowdown often comes down to a single chemical, dopamine. In Parkinsonism, the brain cells that produce dopamine start to die off. And this has a devastating double whammy effect on the basal ganglia. It weakens the go pathway and at the same time strengthens the stop pathway. The end result is that the basal ganglia's output becomes overwhelmingly stop, slamming the brakes on movement before it can even really begin.
Now, this is where it gets really cool. Because by understanding this circuitry, these go and stop pathways, neurologists can basically read a person's symptoms to figure out exactly where in the brain the problem is.
This knowledge basically turns the symptoms into a map of the brain. So, a clinician sees chorea, and their mind immediately jumps to the striatum, which is a key part of that stop pathway. They see the violent flinging of ballism, and they immediately suspect the subthalamic nucleus, that master brake pedal. And if they see the slowness of Parkinsonism, they know the trouble is probably coming from the substantia nigra, the brain's main dopamine factory. It's like a form of incredible clinical detective work.
So in the end, everything we've talked about really comes back to this one central idea: the absolutely remarkable, delicate balance that is required for every single movement we make.
Here's the final equation, the whole thing in a nutshell. If you have too little inhibition, the brakes are off. The motor system gets overactivated, and what you get is a hyperkinetic disorder, too much movement. If you have too much inhibition, the brakes are stuck on. The motor system gets suppressed, and the result is a hypokinetic disorder, too little movement. It's that simple.
What's so amazing to realize is that every single thing you do, from walking across the room to just signing your name, it's not just one command from your brain. It is the result of a perfectly balanced, split-second negotiation between the parts of your brain that are screaming go and the parts that are screaming stop.
It's just an astonishing piece of biological engineering that works flawlessly almost all the time. But after seeing just how fragile that balance is, and the pretty dramatic consequences when it fails, it really makes you wonder, doesn't it? Will you ever think about something as simple as walking the same way again?